directional derivatives and gradients. Okay, so suppose you are on a mountain or on a hill, something like that. This is, suppose, a hill, right? Suppose you are climbing or walking somewhere, you're somewhere there. Okay. And suppose the height of the hill is at each point at x, y. Suppose we are in three-dimensional space. We have x, we have y, we have z. At any point x and y, suppose here is a point x, y, the height of the hill is presented with z equal to f of x and y. So this point is z here, for example. Okay. And you want to know how to determine the slope in different directions. So you want to see, for example, if you're here, if you walk in that direction, if you're climbing the mountain, what would be the slope you feel if you walk, for example, in direction of u? So you want to go in different directions and you want to see what would be the slope you would feel if you are on a hill or if you're on a mountain, okay? So in this case, we have a function from a two-dimensional space, R2, x and y, to R. Okay, and we want to know what is the slope in a given direction. Okay, so suppose this is our domain. This is R2. And each point here, x and y, if I look at the point x and y, I can compute the f of x and y. And the f of x and y, I showed with z, would be the height of this mountain here. So if this point is the point x and y inside R2, if I think about it inside R3 would be x and y and 0, z above that would be the height of this mountain or this hill. Now, I can walk in some direction. I would show it with, say, the direction u. I want to see how the height would change if I walk in direction of u. So if you look at this mountain, if you walk in some directions, for example, if you walk in this direction, the height would decrease, right? We would climb down. If we walked towards this direction, it seems the height really doesn't change much. If we are here, if we walk in that direction, we would go up. If we walk in that direction, we would go down. So the slope in different directions would be different. If we are going up, the slope would be positive. If we are going down, the slope would be negative. So we want to see how the slope, what is the slope in direction of some vector u. One thing we would assume is that we would always assume u is a unit vector. It's kind of like how much your height would change if you take just one step, right? If you want to see if you are going up or down, you can just take one step. That's kind of what it means by taking u to be a unit vector. Just going one step in one direction and see how the slope, what would be the slope, how much the height would change. This is a unit vector in R2. So the unit vector in R2, if I move it to origin, it would be something like this. It would have some angle theta with the positive direction of the x-axis. And whenever it has angle theta with the positive direction of x-axis, I can write down this vector as cosine theta and sine theta. So remember, any unit vector in R2 which makes angle theta to the positive direction of the x-axis is equal to cosine theta and sine theta, okay? And I want to know what is the change of f. What is derivative of f or change of f in direction of u? This is the notation I would use. This kind of means the slope in direction of u, or the change of f in direction of u, or the derivative of f in direction of u. Okay. So how can I compute this? How can I compute this? So derivative of f in direction of u, sometimes this is the notation we use at the given point x and y. Unfortunately, sometimes you write the point x and y down here in some books. In some books, they write derivative of f in the point x and y, and they write down the direction u down here. Sometimes they use a small d to show the derivative. Sometimes they use capital D to show the derivative. And sometimes they use derivative of f in direction of u in x and y. So they all have the same meaning. It's a little hard to understand really which one is the point, which one is the direction. The notation which the book uses is not the best notation, is not the common notation, but I would follow the notation of the book in order to make sure you are not going to get confused. And the notation which the book uses is this one. What is the more common notation which people use? It's this one. So this is more common to use, but the book is using this notation. So in this class, I would use also this notation. Okay. Anyway, so when I have a function f from R to R, like the height function we just saw above some place in R2, we have a heel, and f would be the height. If I want to say what is derivative of f of x and y at the point x and y in direction of u, where u is a unit vector, cosine of theta, sine of theta, what is the derivative? Well, its derivative is defined by this formula. Well, if you're in the point x and y, we can take some small step in direction of u. So it would be x plus cosine theta, y plus sine theta. And then I can subtract f of x and y, and I can divide it by 1. It means how much the function would change if suppose I'm here at the point x and y. If there is this vector cosine theta, sine theta, if I can compute f at this point and I can compute f at this point, if I subtract these two values, it would show how much f the function would change if I take one step in direction of u. Now you might say rather than one step, you might take 1/2 of this step. So I can go in direction of cosine by 1/2 and in direction of u by 1/2. So it would be like looking at the f at the point x plus 1/2 cosine of theta and y plus 1/2 sine of theta, and then subtracting f. But then because it would take half of the time to go there, I should divide it by 1/2 to get kind of the rate of change in that direction. You might say, why 1/2? I can just go a little bit in that direction, say 1/3, and I can divide by 1/3. That would show the rate of change in that direction. Well, to change at some small interval of time. Or I can do even better. I can walk in direction of u for a very short amount of time, say for t seconds, and divide it by t, and I can assume t is very small. I can take limit and send t to 0. That would be actually the rate of change in direction of t. So this is the way to compute this thing, derivative in direction of u. So let's look at one example. So let's say we have a function f equal to f of x and y equal to 4 minus x squared minus 1 over 4y squared. Okay, and suppose we are at the point x and y equal to 1 and 2, and the question is to find derivative of f at this point 1 and 2 in direction of u, where u is this unit vector, cosine of pi over 3, sine of pi over 3. Okay, let's use the definition. So the derivative of f in direction of u at the point 1 and 2 would be the limits t goes to 0 of f at this point 1 and 2 plus t times cosine of pi over 3 plus t times sine of pi over 3 minus f of 1 and 2 over t. Okay, it would be limit t goes to 0 of this thing. What would be the f of this thing? Well, as you can see, if I want to plug in this thing in cosine and plug in this thing into y, it would be something complicated, right? There would be a lot of computations. It wouldn't be interesting to take these limits. You know, I should put 1 plus t cosine of pi over 3 inside x, and then I should square that. I should put this thing in y. I should square that, then divide it by t, take a limit. This is possible, but it would be a lot of computations. But the good thing is that there is a theorem, a chain rule kind of theorem, which says this derivative, as there's an easier way to compute that. What is the easier way? Well, this derivative is equal to the partial derivative of f with respect to x times cosine of theta plus partial derivative of f with respect to y times sine of theta. How does it help? Well, here, rather than computing these limits, I can use this chain rule, new chain rule formula, which follows the original chain rule I mentioned, but we don't need to really derive it. So here, the partial derivative of f with respect to x is just minus 2x. Partial derivative of f with respect to y is minus y over 2. So this chain rule says it would be minus 2x cosine of theta plus minus y over 2 sine of theta, which at this point, x is equal to 1, so it would be minus 2. Cosine of pi over 3 is 1 over 2 plus the partial derivative of f with respect to y is minus y over 2, but y here is 2 itself, times sine of pi over 3, which is the square root of 3 over 2, which is minus 1 minus square root of 3 over 2. That would be the partial, that would be the directional derivative of f. Directional derivative of f in the direction of u. That's the answer. As you can see, it's a lot easier to use this formula. Okay. Now, the next thing I should talk about is the gradient of a function. Of a function. Okay, so in the homework, we had so-called the level surfaces. If you remember, you were supposed to sketch the level surfaces of a function of two variables. So there is something about that. So if we have a function of two variables, for example, f of x and y is equal to 4th root of, say, 16 minus x squared minus y squared. We had a function like this. And I wanted you to sketch these level curves, level surfaces. So what we should do, what it means is that we should set it to be equal to z. We should look at the three-dimensional space, x, y, z. If we square both sides, we get z squared is equal to 16 minus x squared minus y squared. It means x squared plus y squared plus z squared equals to 16. Now, a question which you have similar this question in your homework is to draw the level surfaces. For example, for z equal to, say, 1, 2, and 3. You should say if z is equal to 1, it means x squared plus y squared. Oh, I should consider a three-dimensional case. Sorry.